Welcome to the EFI Hardware Podcast. Just a heads up, you are hearing AI voices, but don't worry, the information we're sharing today, it's all been checked, double-checked, and approved by real, experienced humans.
That's right. We're here to dig into engine management topics and hopefully make them a bit clearer.
And today's topic is, well, it's fundamental if you're moving towards EFI or just looking for more performance, upgrading your engine's ignition system.
Yeah, this definitely pops up when people are converting older, maybe carbureted engines. But honestly, the ideas we're talking about apply pretty much across the board for getting more out of almost any engine.
So our plan today is to kind of walk through the options, the benefits, what you need to think about if you're considering an ignition upgrade. We'll break it down.
Sounds good. Let's start where a lot of older engines begin, the traditional distributor system.
Right, the purely mechanical setup.
Exactly. Think about it. You've got this distributor driven usually off the camshaft. Inside, you've got weights flying out with RPM for mechanical advance, and often a vacuum canister pulling on a plate for load-based advance.
All mechanical linkages and springs doing the work.
Totally. And it's responsible for when the spark happens and which cylinder gets it.
But those old systems, they have some real limitations, don't they?
Oh yeah. The biggest one is probably mechanical instability or slop. Think about the timing chain stretching, gears wearing, even the distributor shaft itself having a bit of play.
All adds up.
It does. And it means the timing signal the distributor sees isn't perfectly steady relative to the crankshaft. You put a timing light on it, and you can actually see the mark jump around, maybe 1, 2, even 3 degrees or more.
And that jumpiness, that variation, that's bad news for precise tuning.
It really is. Because if you're aiming for, say, 36 degrees of advance under power, but it might randomly spike to 38 or 39 because of that slop, well, that could push you into detonation if you're near the edge.
So you end up having to run less timing overall, just to be safe, leaving power on the table.
Precisely. You build in a safety margin that costs you performance and potentially efficiency. Plus, you just can't fine-tune the curve with springs and weights the way you can electronically. And, those mechanical parts wear out over time.
Which brings us neatly to the big advantage of electronic control via an ECU. What's the core benefit?
Precision. Absolute, rock-solid timing precision. When the ECU commands 36 degrees, it triggers the spark at exactly 36 degrees relative to its trigger input. Every single time for those conditions. That timing bounce we talked about, gone.
That sounds like a huge difference.
It is, because now you can program a really detailed ignition map. Think of a grid with RPM on one axis, engine load on the other. You can dial in the perfect timing for idle, cruise, light throttle, full throttle, everything in between. Hundreds of points, potentially.
Instead of just a curve dictated by springs and vacuum.
Exactly. And running that optimal timing, not a compromised safe timing, means more power, better fuel economy, especially at part throttle, and often cleaner combustion, too. It all stems from that core accuracy.
Okay, so the ECU figures out when to fire with amazing accuracy. Let's talk about how the spark actually gets to the plug. There are different ways to handle the output, right?
Right. The ECU sends the fire signal, but how that energy gets delivered varies. The simplest step up, especially for conversions, is often using a locked-out distributor.
Where you basically disable the mechanical advance parts inside the original distributor.
Correct. You fix the internal mechanism so it doesn't advance on its own. The ECU takes over all the timing calculations, but the distributor cap and rotor still handle sending the torque to the correct cylinder's plug wire.
So you get the electronic timing brain, but still use the old distribution method.
Pretty much. It's an improvement for sure, gets you that ECU control. But you still have the cap, rotor, and plug wires as potential points of energy loss or issues, especially at high RPM. Some companies even sell distributors made specifically for EFI that are essentially locked-out units ready to go.
Okay, what's the next step up from that?
That would typically be a waste spark system.
Is that the one where a single coil fires 2 plugs at once?
Yeah, exactly. Cylinders that are companions, meaning they are 360 degrees apart in the firing order, so one's on compression while the other's on exhaust, share a coil. The coil fires both plugs simultaneously. The spark in the cylinder on its exhaust stroke is wasted. It doesn't do anything.
It's a bit odd. Why do it that way?
The big advantage is dwell time. Dwell is how long the coil gets to charge up with energy before it fires. More dwell generally means a hotter, longer spark.
Okay.
Now think about a V8 with a single coil and distributor. That coil has to charge and fire 8 times every engine cycle, 720 degrees of crank rotation. With waste spark, say you use 4 coils for the V8, each coil now only fires 4 times per cycle.
Ah, so each coil gets twice as long to charge up between firing events.
Spot on. Especially at higher RPMs when time is short, that extra dwell time lets the coil build more energy. It's really helpful for lighting off the mixture reliably under load.
Makes sense. But then there's the top tier, right? Coil-on-plug.
Yep.
Direct fire, or coil-on-plug COP. That's generally seen as the ultimate setup for high-performance EFI. Each spark plug gets its very own dedicated ignition coil mounted right on top of it.
No plug wires needed then.
None at all, which is a big plus. You eliminate the energy loss and potential failure points of high-tension leads. The energy goes straight from the coil into the plug. Maximum efficiency.
And I bet the dwell time situation is even better.
Oh, massively better. This is the key advantage. With one coil per cylinder, each coil only has to charge and fire once per full 720-degree engine cycle.
So in that V8 example, instead of one coil firing 8 times or 4 coils firing 4 times each, you have 8 coils each firing just once per cycle.
Precisely. That gives each coil a huge amount of time to saturate to build maximum energy. And that is absolutely critical for engines running high cylinder pressures, think high compression ratios, or especially forced induction like turbos or superchargers.
Because it's harder for the spark to jump the gap under high pressure. Much harder. You need a really strong high-energy spark to reliably ignite the dense mixture. COP systems, especially when paired with high-performance coils like, say, the Bosch Motorsport units, which are designed for this, provide that capability. Getting those coils and the right connectors for them is something specialists like EFI hardware focus on. It's about ensuring that strong spark happens every single time, even under boost.
Okay, that makes sense for the output side, but none of this works if the ECU doesn't know when to fire. That brings us to the trigger system, the input side.
And this is probably the most critical piece of the puzzle. Get the trigger system wrong and nothing else matters. It tells the ECU engine speed and, crucially, engine position. If that signal is noisy, inaccurate, or missing teeth, the ECU is lost. It can't time fuel or spark correctly. So many issues trace back to trigger problems and conversions.
So what are the common ways to get that trigger signal?
Well, the most basic electronic step is often using a pickup inside the distributor. Could be a magnetic reluctor, could be a Hall effect sensor. It reads teeth or slots on a wheel attached to the distributor shaft.
What does that tell the ECU?
A simple setup might just give 1 pulse per cylinder firing event, or maybe per TDC event. This gives the ECU RPM data, how fast the engine is turning. And it knows when a piston is near TDC.
But it doesn't know which piston is at TDC.
Not usually, no. Not without more information. And that's the limitation. Without knowing the specific cylinder, the ECU can't do true sequential fuel injection, firing each injector individually right before its intake valve opens. It needs to know which injector's turn it is.
And it also prevents using coil-on-plug, right?
Yeah.
Because it doesn't know which coil to fire.
Exactly. You're limited to batch fire injection, firing injectors in groups, and typically distributor or waste spark ignition. And importantly, even with an electronic pickup in the distributor, you still have that potential timing instability because the distributor is driven by the timing chain and gears. That mechanical slop can still affect the signal timing slightly relative to the actual crankshaft position.
So for the best accuracy, you need to read directly off the crank.
Yes. That's where crank trigger systems come in. Pretty much universally recommended for performance builds. You mount a trigger wheel directly to the crankshaft, usually on the harmonic balancer, and a sensor reads that wheel.
This bypasses the timing chain, the cam drive, all that.
Completely. It gives the ECU a direct, unfiltered view of exactly where the crankshaft is and how fast it's spinning. This eliminates the timing variations caused by the drivetrain slack. Absolutely vital for high RPM stability, or engines running lots of boost or high compression where timing accuracy is paramount.
What do these crank trigger wheels look like?
Often they have a pattern of teeth. A very common one is a missing tooth wheel, like maybe 36 teeth evenly spaced, but with one tooth deliberately removed. That gap gives the ECU a reference point once per revolution. Or you see systems like MSD's flying magnet wheels, which use magnets embedded in the wheel.
And a sensor picks up these teeth or magnets.
Yeah, right. A pickup sensor could be a variable reluctor, VR, or a Hall effect sensor is mounted near the wheel. Getting this mounting right is critical. It needs to be absolutely rigid. Vibration can cause the sensor to move relative to the wheel and create false signals or timing scatter.
And the distance between the sensor and the wheel matters too.
Hugely. It's called the air gap. Too close or too far, and the signal quality suffers. You have to set it precisely according to the manufacturer's spec. That MSD example, they recommend something like 50 to 80 thousandths of an inch. Getting the bracket stiff and the gap right is key.
Okay, so a crank trigger gives super precise crank speed and position within 1 revolution. But we still need to know which revolution we're on for sequential fuel and COP, right? The 720-degree cycle thing.
Correct. The crank trigger tells the ECU we're at TDC, but not whether it's TDC compression or TDC exhaust for cylinder #1. For that, you need a second signal, usually called a sync or cam sync signal.
Which tells the ECU which half of the 4-stroke cycle it's in.
Exactly. It provides 1 pulse per camshaft revolution, which is 1 pulse per full 720-degree engine cycle. This signal can come from a sensor reading a single tooth or feature on the camshaft itself, or sometimes by using a simple 1 pulse per rev pickup in the old distributor housing, since the distributor spins at cam speed.
And combining that crank trigger precision with the cam sync signal, that's the magic combination.
That's the ideal setup, yes. Crank trigger plus cam sync gives the ECU full information. Precise crankshaft position and speed, plus the engine's phase within the complete 720-degree cycle. That unlocks full sequential fuel injection and allows direct fire coil-on-plug ignition. It gives the absolute most control.
Right. So let's say you've decided on your ignition setup, maybe crank trigger, cam sync, and COP coils. You're building out the whole EFI system. What other key sensors does the ECU need?
Well, an ignition upgrade usually goes hand in hand with a full EFI conversion or upgrade. So yeah, you need sensors. Temperature sensors are vital. Intake air temp, or IAT, and engine coolant temp, ECT. They let the ECU adjust fuel and timing for air density changes, and engine temperature crucial for starting, warm up, everything.
And pressure sensors.
Absolutely. A manifold absolute pressure sensor, MAP sensor, is usually the primary sensor for determining engine load. The ECU looks at MAP versus RPM to find the right spot in its fuel and ignition tables.
What about for engines with individual throttle bodies, ITBs? MAP signal isn't great there sometimes.
True. For ITBs, the throttle position sensor, or TPS, often becomes the primary load input. That's called alpha N tuning using throttle angle, alpha, and RPM N. But even then, you often still want an MAP sensor for barometric pressure correction or other compensations. And you need a TPS anyway for detecting throttle movement, for acceleration enrichment, and for idle control functions.
Makes sense. And the one everyone talks about for tuning.
The wideband oxygen sensor, or lambda sensor, essential. It measures the actual air-fuel ratio in the exhaust, giving you real-time feedback for tuning. Plus, it allows the ECU to run in closed loop, constantly fine-tuning the fuel mixture to hit your target AFR. Absolutely critical for accuracy and consistency.
So gathering all these bits, the right coils, the trigger components, the sensors, it's important to use quality parts that work together.
Oh, definitely. You need reliable, high-performance coils, like those Bosch Motorsport ones we mentioned earlier that can handle the demands. You need robust electrical connectors for everything, the sensors, coils, injectors, ECU that can withstand heat and vibration. Getting accurate sensors, MAP, TPS, IAT, ECT, the wideband O2 is non-negotiable. These aren't areas to skimp on.
Sounds like you need a supplier who knows this stuff.
Precisely. Finding specialists who offer these types of components, the right coils, the connectors, the specific sensors you need, plus potentially related fuel system parts like injectors, fuel pumps, throttle bodies, makes the whole process much smoother. You want parts designed for the job, parts you can trust. That's exactly the kind of area EFI hardware operates in, providing those critical pieces for performance engine management.
Okay, so let's kind of pull this together. Upgrading the ignition, moving from mechanical to electronic control, especially going to a crank trigger and maybe COP, it offers some serious benefits.
Huge benefits. You get that precise, stable timing control, which is safer and unlocks performance. You get way more tunability across the whole operating range. You get the potential for much higher spark energy for difficult combustion conditions. And generally, you get better reliability than old mechanical systems.
It lets you really dial in one of the most critical aspects of how your engine runs.
Absolutely. It's definitely more involved than just dropping in electronic ignition module in place of points. But the level of control and the performance potential it unlocks is just on another level.
It requires careful planning and choosing the right components that all work together. Trigger, coils, sensors, ECU.
For sure. Doing your homework and selecting quality parts is key to getting the most out of your engine, safely and reliably. And remember, all this info we've discussed is human vetted and based on solid principles.
So here's something to think about. With this kind of precise electronic control over ignition timing, control that just wasn't possible 50 years ago, how might that let us rethink engine design itself, or maybe explore alternative fuels in new ways, knowing we can manage combustion events with such accuracy?
Yeah.
What new possibilities does that unlock?